Good morning, everybody, and good midnight to Raghav. So welcome to this uh, guest lecture, and it's a very special one. It's a very special one because you know, the person who is doing this session, I met him when he was slightly older than you guys, and he was there for one of the residential camps that we do. And I've seen how his love and passion for math has grown in leaps and bounds. So I'll just do a very informal introduction about Raghavendra. Raghavendra has been very passionate about math right from childhood, and he was he was fond of primes, and he asked very deep questions about primes, like what can be the maximum prime number gap that can exist, or can there be a prime number which is so large, and so on. And these questions came from him when he was a young child, and he continued his exploration in primes. And when he was around high school age, by I think ninth or 10th standard, he had come up with around 25 conjectures just related to primes. So all of you by this time, you know what conjectures are, and I think Sundar did a couple of sessions on conjectures and things which are not proven. So he came up with 25 conjectures, and because he was a cricket lover, he named those conjectures after something related to cricket. I remember Raghavendra, like the square cut conjecture, and something of that sort and all. Uh, I think at that time he felt that that was a groundbreaking, discovery. But some of those conjectures were already, you know, existing. But then those conjectures were come up by people like G.H. Hardy and Littlewood, who worked with Ramanujan. So his conjectures, even though was a rediscovery on his own, they were highly profound, and it was not very easy to come up with these ideas. So Raghavendra is a very good combination of the logical side, the math, as well as the creativity. And through this session, he's going to try to show the creative aspect in mathematics. But right now, he is doing his undergrad from University of Illinois, Urbana-Champaign in the US, and he's doing his undergrad in math. Um, and he's, apart from that, he loves tabla. He loves music. He loves cricket for sure, and he's very emotional about cricket. I can see that from his Facebook posts. And then he loves to interact with students like you guys. So without taking more time, I'll hand it over to Raghavendra. Raghavendra, over to you.
Thank you so much, Vinay sir, for that very nice introduction. I'm always humbled by the way you present me. It's been a very nice journey with Vinay sir, with the many camps that Vinay sir does. I think the first time I ever attended a camp like that was in 2013, when I was just about 14 years old. And it's really an honor for me to be here and to talk to all of you. I just finished my semester yesterday. So this is like an end of semester celebration where I get to do something that I really, really like doing. Of all the things that I do in my life, the thing that I love doing the most is interacting with other people who like math. And if they're all younger to me, I like it even more than if they're older to me. So it's just a fact that although I really have some incredible professors and I love talking math with them, it's very, very nice to talk math with budding mathematicians like you guys for a very important reason, which I will come to very soon. Talking a little bit about me, I think some of you here already know me. I am originally from Karnataka in India, and I came to the US in 2019. I am currently pursuing a degree in mathematics as my major and computer science as my minor at University of Illinois here in Urbana-Champaign. It's been a wonderful experience doing an undergraduate degree here. Although the last 1 year was quite different owing to the pandemic and all of that, it's been a good experience. I haven't left this country for almost 2 years now. And I would like to tell you all that one thing that can keep you going in these very hard times, I feel this important to let you all know, because I know we're all going through different things, is that as long as you're passionate about what you do and you're very sure of what you want to do, you can somehow make things work irrespective of what the circumstances are. I remember there was a point of time, I think in 2017, when I was so desperate to attend the camp in Chinmaya Mission, which Vinay sir does every year. And I was so crazy about math at that point of time that I was willing to go there no matter what, whether it meant traveling on a train, in the third class compartment, or anything like that. And even in these times where classes are online, the only thing that keeps me going is I still ask myself, do I still love what I'm doing? Do I still love math? Do I still love all my classes? And it's still going to work out well. Try to get motivated, try to look within yourself for inspiration. I think in these times when we are so far away from the rest of the world, we have to look within and take inspiration from ourselves. Okay, so that said, what I'm going to talk about today will completely depend on one very important word. And according to me, that word is the single biggest tool when it comes to learning. And that word is creativity. It's a very simple word in English, but it had a huge influence on me. A talk which I saw when I was around your age. It's a talk by Ken Robinson. It's a TED talk, and the talk is called How Schools Kill Creativity. Now, I don't really believe that schools will kill creativity, but in that talk, he has addressed a lot of really important aspects about creativity. Creativity is something that is innate and is the single biggest reason why I like interacting with people like you. So that's the reason why I enjoy interacting with people like you, because I feel the creative capacity of a young mind is unbelievable. There are a few very lucky people who are able to be creative even as they grow older. I feel a lot of world-class mathematicians have to be creative to do what they do, but in a young mind, it's so pure, and that creativity is incredible. So what is this whole thing about creativity, and why am I here to talk about that with you? Most of you might be knowing this. When Thomas Alva Edison, he discovered the light bulb or electricity or whatever that is, there were a lot of things that didn't work out for him before he came up with the final invention. There were over 900 times that he went wrong. Steve Jobs, when he came up with the first ever iPhone way back in 2007, it's a well-known story that when he was doing his final presentation in front of half of California's biggest computer scientists and most of the world watching it, the model that he was showing wasn't even foolproof. There were so many things that could have gone wrong, but he still went ahead with it. Most of the incredible discoveries that have happened, for example, J.K. Rowling, who is the author of the world famous Harry Potter series, she was rejected by 12 authors, by 12 publishers, before finally somebody agreed to publish her book, and now it's the most sold English literature series in the history of the world. So what it tells is, the one thing that is common among all great people is that they are not afraid of being wrong. They're not afraid of failing. And why is this connected to creativity? I feel every single child is born with some creative talents given to them, whether from their parents or from God or whatever you believe in. I feel everybody's born with some level of creativity. It's only, the problem is to stay creative as you grow older. Because what other people say, what you learn, what you're taught, what you're influenced by can sometimes shape the ability to be afraid of being wrong. Because I feel creativity comes when you are not frightened of making a big mistake. You're not afraid of being wrong. You are willing to give it your best shot without worrying about the outcome. That is when creativity is at its best. Srinivasan Ramanujan, who I genuinely believe is among the top 3 mathematicians of the last 100 years, the thing about him was that his creativity was so good, and his knowledge pool at that time, before he went to Cambridge and worked with Hardy, there were a lot of things that he didn't know. So he wasn't even afraid of being wrong, nor was he afraid of being right, because there was a lot of gray area. But because of his creativity, because he was not afraid of making a mistake, he was able to make some breakthrough discoveries in mathematics. And that is not, it's not true only with mathematics. I think it's true with many different fields as well. Sport, for example, I think some of the greatest soccer players some of the greatest cricket players, they are what they are because they are creative. Okay, so I am really honored to give this talk here before you to talk about conjectures. And the one thing about conjectures, or when it comes to theorems, or when it comes to axioms, some of us might be knowing about Euclid's axioms or postulates or whatever you call them. I feel people who come up with them are coming up with them without having any expectation. They're not afraid of making a mistake. They're not afraid of saying some rubbish, which might be wrong. And what happens is, if you make 100 such rubbish statements, there is a chance that one of them is correct. It's a very cliche thing to say, but I think that people who are creative and are successful are actually the laziest and the most stupid people, because they make so many mistakes that nobody else knows about. They'll only make one thing correct and they'll be known for that. There's a very famous quote which says, if you had enough number of monkeys available and you gave each of them a typewriter and you randomly made them sit in a room, one of them would ultimately type out the entire Julius Caesar play by Shakespeare, because the probability that somebody will exactly hit the right key is very high. So if you're not afraid of being wrong, if you're really not afraid of being judged by anybody, and you keep trying to come up with something new, there is a very high chance that you will eventually come up with something that is unknown. Another quote, if you don't try, it's always a no. That's something you should always remember in life. Sometimes we're afraid to try things, but we should realize that if we don't try things, the answer is always a no. Sachin Tendulkar, one of the most famous cricket players of all time, once told that whenever he was given an opportunity in his life, I think his journey started when he was 9 or 10 years old. He started playing cricket and then he had to play for Mumbai when he was 14 or 15. Ridiculous person. He said that the reason he was successful was each time somebody told him to try something, he would always say yes. Always. If somebody told him, go to that tournament and play there, he would say yes. Go to this overseas tour and go and play in Australia. Yes. Go join this coaching, play 14 hours a day. Yes. Why did he do that? Because he felt when you say no, you are limiting the outcome by your reply, right? You are now in control of your future. Let's imagine the moment you say no, you are deciding that this will not happen. Okay. When you say yes, you aren't actually deciding that it should happen, but you are allowing the rest of the universe to conspire to make it happen, if at all it should happen. If you say no, that's it. You're finishing it then and there. But if you say yes, maybe it can happen. Maybe 1 in a million situation it might happen. Maybe 1 in a billion, but it's still more than zero. 1 out of trillion is more than zero. So you're still giving yourself a better chance when you say yes. Okay. So let me narrate a small incident. I had a very interesting childhood when it came to mathematics, because I think I had some sort of a love-hate relationship with mathematics. When I was about 7 years old, my parents started giving me some long multiplication problems in my summer vacation, which I wasn't really too, excited about, because I could see that none of my other friends had to do such things and people were playing games, and I felt a little irritated by it, but it was fun. I still remember doing those 8x8 multiplication problems, and it was a lot of fun doing all that. And then there was a long period in life from around 3rd grade or 4th grade all the way up to 6th or 7th grade where I didn't really think that much about mathematics other than whatever was taught in school. I was sometimes, my parents were informed that I sometimes disturb the class with questions, or that I cannot sit in one place for a long time, or I disturb the rest of the people or whatever. So it kind of demotivated me, and I felt, okay, if this is what these people want, I'll just sit and I'll do whatever they tell me without doing anything more. Then when I was in 9th grade, something very interesting happened. One of my math teachers, who wasn't actually teaching me, she was teaching the other class, she gave me a book on number theory. I don't exactly remember what that book was. It was something to do with numbers in general. And she told me, maybe you would like math, so you can read this book and you'll find things interesting in that. I was fascinated. I always had some sort of an interest in prime numbers, partly maybe because I was born on March 13th, 1999, where March is the prime 3rd month, and then 13 is a prime number, and 1999 is also a prime number year. If you want some more information, I live in house number 37, which is a prime, and I was the 7th member of the family, and apparently born at 3:47 p.m., which are all prime numbers. So whatever. So I think somebody had told all this, or maybe I found it out, and I really had a good feel about prime numbers in general. And one more thing that was told to me as a child was that there are a lot of things in prime numbers which are not known. Okay. So me being the lazy person that I am, I said, hey, this looks like a field where not too many things are known. So maybe I don't have to try that hard to come up with something new. That was what I thought at that time. Now I know that a lot of things are not known, because actually things are difficult to be known. So it's not that nobody tried. A lot of people have been trying for 200 years or so. And the reason not a lot of things are known is because it's actually a very complex area. So just because something is not known, it doesn't mean it's easy to get. Okay, whatever. So I was really interested in primes, and I looked at this book. there was a chapter on prime numbers, and I straight away went into the chapter of prime numbers, ignoring everything else. No geometry, don't want to look at trigonometry, don't want to see anything else, just want to look at prime numbers. And I started looking at a few numbers, and I suddenly started noticing a very simple pattern in numbers. I thought to myself, hey, if I add two primes, as long as they are not two, so all of us know that 2 is the first prime number, and then you have 3, and then you have 5, and you have 7 and 11 and 13 and so on. I realized that if I pick any two primes other than 2 and add them together, I will always get an even number. So at that point of time, it's a very silly thing, because we should probably know that the sum of any two odd numbers should be even. But it didn't hit me that all prime numbers other than 2 are odd. So that's why it's working. But I just picked random primes and I was adding them together, and I was getting even numbers, right? So you do 3 plus 7, you get 10. It's an even number. You do 11 plus 29, you get 40, which is an even number. So I kept doing that. Then I started noticing that I was getting a lot of different even numbers each time I picked two prime numbers and I added them together. So I wasn't getting the same even number each time, right? So if I do 3 plus 7, I'm getting 10. If I do 7 plus 7, I'm getting 14. If I do 13 plus 7, I'm getting 20. Or if I do 61 plus 37, I'm getting 98. So I'm just getting these random even numbers if I pick two prime numbers. I know all of this sounds very silly, but yeah, somebody's written in the chat. Somebody is way ahead of all of us. Okay. So I started asking myself a question. If I can generate these random even numbers when I pick two primes and add them together, is it possible that I could pick any even number that I wanted and split it up as two primes? Right? So I tried, let's see, 12, say 7 plus 5. Okay. So what about 18? Okay, it looks like 13 plus 5. What about 36? I said, it's a slightly larger number, 36, 31 plus 5. Then I thought, okay, maybe everything has 5 plus something in it. So let me pick something which is different. Let me go with 38, which is 31 plus 7. So I started noticing that, yeah, there is seemingly no pattern here. You can still somehow get two prime numbers to add up to some random even number of your choice. So at that time, I had just started learning computer programming. I was given a brief introduction to it. My uncle was teaching it to me, and there was some online course by MIT that I was taking at that point of time, and I knew a little bit of Python programming. So what I thought is, okay, let's, rather than checking this out manually, because there are so many numbers, right? I think I manually checked for every even number from the number 4, which is 2 plus 2, all the way till whatever is 100. And I found out that it's still working, but I said, okay, let me try for something bigger by coding it somewhere. So I wrote a code, and it ran for a very long time. And every single even number, all the way up to, I think, 100,000 or something, was still a sum of two primes, which was really astounding for me at that point of time. And I thought I'd done a discovery. Until the next morning, for that one night, I really thought I had done something incredible. But I think a couple of people have put it in the chat. It is the well-known Goldbach conjecture. It's such a famous problem. I think it's probably the most popular conjecture. That's a matter of opinion, but I genuinely believe, because I've heard it a lot of times in many different talks. Many professors, not even number theory professors, people who talk about algebra or analysis, they just randomly bring up the Goldbach conjecture. As a joke, one of my professors here at UIUC, in my first class, this was a year ago, before the pandemic, on day 1, we were given 5 questions as homework, out of which the first 4 were kind of silly, prove that the sum of any two even numbers is an even number, but you have to prove it, with some rigor, whatever. And the last question was the prove that a sum of any even number can be written as sum of two primes, as a joke. But I quickly asked him, isn't this some well-known problem or whatever? And I spoiled his moment, because I think he was hoping all of us would try. And then the next day, is my audio, can others hear me clearly? Okay, good. Okay. So I think he was trying to play a prank on it.
I'm unable to hear audio.
Oh, okay.
I'll take care of that, Raghav. You can.
Sure. So that's what happened. And this is something which is not known by anybody. People believe it to be true. A lot of computers have verified this to, I think, 10 to the power 17 or something like that, which is a crazy number, right? It's what, 100,000 times 1 trillion. And it still works remarkably. You pick any even number of your choice, you can still split it as a sum of two primes, right? So again, coming back to 2015, I think it was, maybe end of 2014. And I was a little bit disappointed. I said, hey, for a moment, I was assuming that I've come up with some discovery on my own. but this somehow doesn't seem to be my own. It's already discovered, and I was a little dejected. But there was something that really gave me hope at that point of time. And this is something which is very important. And I want all of you to keep this in mind when you try to be creative or when you try to come up with something new. Remember that this world has been running for a very long time, right? We are just born now. I think there is a calculation that you can look at where if you were to measure the entire Earth's lifespan as 1 year, starting the Jan 1st is the birth of the Earth, and whatever December 31st is where we are now. I think the time when you were born or some of your ancestors were born or whatever would be literally in the last microsecond on December the 31st after 11:59 p.m. So it's such a small fraction of time when you look at the entire totality of the Earth's existence. And there have been a lot of people before. There have been a lot of things that have happened on this planet before you came. So as time passes, it's more and more less likely for you to come up with something new or something that has not been done before, especially in a field like mathematics, which is so abstract and closed. For example, when you look at some other fields like machine learning or things like that, which are changing every year or almost maybe every month, there is a lot of scope for discovery. But math is something which will stay true no matter what, right? It's something which once Euler proves something, once Erdos proves something, once Ramanujan proves something, these things will stay true forever. Once you yourself prove the Pythagoras theorem or whatever, it will stay true. It is a very, what's the word for it? It's not very, the entropy of the thing remains the same. You cannot keep changing it. There's very little disorderness in mathematics. It's quite well structured. It's almost like a game of chess. It's very perfect. So it's very hard for you to come up with something which has never been looked at before. But hey, one thing that gave me hope at that point of time was I asked myself, did I know, first of all, did I know the Goldbach conjecture is the one thing, but did I know of Goldbach himself? Had I ever heard of him? No, I wasn't half as smart as you guys, because all of you before you turn 12, you know Goldbach, you know Goldbach's conjecture, and you know a lot of other things. I had no idea who Goldbach was. I absolutely didn't know what he had done in his life, let alone know the Goldbach conjecture. So I thought to myself, okay, so I came up with something which was already known, but I did it without knowing that it was already discovered. I did it without taking help from somebody. So I felt, okay, maybe that's not a bad thing. Right now, my duty then is to make sure I don't get frightened of the same thing happening again, because this might keep happening for the rest of my life, right? Each time I come up with something new, for a short while, I might think I've come up with a discovery, but then I might find out that somebody else has come up with it. So I told myself, this is a lesson to be learned. Two lessons to be learned. First, do not be afraid of being wrong, because creativity will be curbed completely if you're scared of being wrong. And creativity is the single biggest weapon if you want to come up with something new, right? Creativity itself is coming up with something new. So if somehow I had gotten scared at that point of time, maybe I would never even want to do a degree in math, or I'm trying to, I hope of doing a PhD in math, or right, doing research in math. How will you do such things if you're scared of being wrong, or if you're worried that whatever you do has already been done? So I told myself not to be scared. And the second thing is to wait for that one moment where I might hit something which is not known. If you keep trying, eventually there is a higher chance for you to hit one conjecture or one idea or even a one brainwave moment where you have thought of something which has not been thought of before. It is possible, because the number of possibilities for ideas is infinite, genuinely infinite. You can think of so many things, and the number of people who have lived before you is finite. So by the pigeonhole principle, if you try hard enough, you should probably be able to come up with an idea which nobody has come up with. I hope you are all familiar with the pigeonhole principle. Has that been discussed in any of your sessions? Okay, good. So by the pigeonhole principle, because the number of ideas possible is more than the number of people that exist, you might just come up with something that is not known. Okay, that's one thing. So what happened after the Goldbach conjecture thing? I went on this complete mental spree where I told myself, I will keep trying, I'll keep trying, I'll keep trying. So I think the next 4 or 5 months, or maybe even 6 months, I tried a lot of different conjectures. I tried a lot of different ideas, and then I compiled them. I wrote them as a 25 conjectures of a 15-year-old, and I tried to get them reviewed in many different places. And one of those places, coincidentally, was this very university where I'm studying now, because I think some of the finest mathematicians who actually looked at my work back then were people who were professors here. And my life has been in such a circle that eventually I have come back to the same place, and I'm actually working with some of those people now. So I consider myself really fortunate. But at that time, those conjectures I felt were quite new maybe, but most of them, as Vinay sir already mentioned, were things which were already unknown. So we cannot say those were things which were known because it wasn't solved, but other people also knew that these things are conjectures. So what's the difference between a conjecture and a theorem? A conjecture is something which is assumed to be true but is not yet proved, or maybe assumed to be not true but not yet proved or disproved. It's something which is up in the air for anybody to be looked at. You prove it, you're a genius. You don't prove it, you're still a genius, because in math people like it either ways. As long as you prove something concrete, they'll be happy with you. You go to a world-class mathematician and you prove that his discovery was wrong, he'll probably make you his colleague, because that's how it works, right? It's almost like Shankaracharya and somebody else having a discussion on the Dvaita philosophy and the Advaita. Whoever loses becomes the pupil of the other guy. There is no ego here. Everybody is after knowledge. Nobody's bothered about who is right. They just want to know what is right. So I'm sure when Pythagoras came up with this theorem, if somebody else went to him and told him, hey, this is rubbish, this is not true, I'm sure he would have been very happy to know it. Or Fermat's last conjecture, which is now a theorem, if somebody disproved it, the mathematical community would have been as overjoyed as they were when it was proved. Another thing, an anecdote that I want to share with you, which was narrated to me by one of my professors very recently, this Goldbach conjecture, this incredible puzzle, which has been keeping mathematicians, interested for over 250 years now. There was this one legend. I don't know whether to call him a legend or an idiot. You guys decide what it is. He proved it, apparently. He wrote a huge proof of this Goldbach conjecture. He also disproved it using another huge proof. So, I think you all are smart enough to know one of those has to be wrong, but he wasn't. He sends both those proofs, one entire proof of the Goldbach conjecture, entire disproof, is that a word? Whatever, contradiction to the Goldbach conjecture. He sends both of those things to the same journal for publication. So you all are aware that you could send your work to a journal and it can get published if it is reviewed by somebody and if people feel that it is an idea worth publishing. He sends both of those into the same journal and he says, I therefore conclude that mathematics is inconsistent. You can actually prove and disprove something at the same time. So there are these ridiculous people who try to say that math itself is inconsistent rather than admitting that they probably did a mistake in one of their proofs. The same thing happens with the Riemann hypothesis as well, which I'm sure some of you are aware of. It's another very famous problem, and quite a few people try to prove it as well as disprove it, whatever. So that guy, I'm sure both of his proofs should have been wrong, because if either of them was right, he would probably have done something which was incredible, but whatever. These sort of things happen. What I'm saying is, you don't have to prove something to be famous. You can actually disprove something as well, and it will be equally incredible. Okay, so now I wish to discuss with you some of my conjectures, which aren't as well known as the Goldbach conjecture and aren't directly already known. So it's very difficult for me at this stage to come up with something which has never even been imagined. That's not possible. But I at least have a few conjectures which haven't been explicitly considered to be conjectures. Maybe people have thought of them. Maybe they are a corollary of some other result, assuming something else, something like that, vaguely thought of, but not done by anybody else, doesn't have anybody else's name on it, like the Goldbach conjecture or the Chen's theorem or the Riemann hypothesis or the Hardy-Littlewood conjecture. These are things that have been copyrighted by some legendary mathematicians. So I think I have a few of my conjectures which I can share with you, which aren't probably that well known. Maybe some of you here might tell me that, hey, actually I read this last week, it was published. That's highly likely because it's an ever-changing field. Every month somebody will come up with something new. But to make things a little interesting, rather than just tell them, I actually want to show you those conjectures in mathematical form. Okay. Some of you might be new to this sort of thing. Some of you might have seen this kind of thing. I actually want to show it to you the way you would probably see it in a paper or in a journal, if at all, because that's what I'm trying to work towards, writing this in a good form, show it to a mathematician or send it to a journal. So I want you to understand how these things are presented in the mathematical world, because I assume most of you might also want to pursue math either as a passion or as a career option, or some of you might be wanting to do a degree in math, which I highly recommend. I had second thoughts about some of those things, because when I started off my degree, I thought prime numbers are the only things that I like. But I think right now I've found out so many other things which I like equally, and some things which I like even more. So I think a math degree is highly recommended. There's nothing to be scared of. So I can tell this to you now because there's only 1 or 2 more courses left for me to do. And so far, everything that I did, I had a great time and enjoyed a lot. So nothing against that. So let's see. Before I show that, I want to ask you, how many of you have actually ever read or seen a math paper? If you have, raise your hand. Let's see. What's the count? We have 3.
Sorry, Raghavendra,
Yes,
do you
sir.
want to clarify the difference between a math article and a math paper?
Sure. So a math article, I'm sure all of us have seen. You can even see it in a high school school magazine. You can write a math article. You can write about why pi is my favorite irrational number. You write an article, or you can say how to teach mathematics, or some of you might have heard my book, which is titled Math, a Subtle Language of the Universe. That's just basically a collection of many math articles that I wrote, sort of. It's not actually a rigorous math paper. When you talk about a math paper, it's not even a math textbook. It is talking about a new discovery, either a conjecture or a theorem with proof. And it's written in a very academic form, which will have an introduction, proofs, you'll have some conclusion, and then you'll have some sources which you have cited. There'll be an abstract, there'll be some acknowledgements to your professors or to your parents or whoever it is. So it's more of a very academic form. That's something which you'll see at a conference, right? If you've ever been to a math conference, I think in India there are things like AMTI or whatever. Some people present their math papers there. Or if you go to a number theory conference or an algebra conference, when somebody presents their work and you write it on LaTeX. So these are some key words associated with math papers. Yeah, so I think quite a few of us have seen it. And let me actually now share my screen, and I will show you something that I'm currently writing. And it's almost in some sort of a paper form. And there are a lot of things in it which might look confusing to you, but we will only focus on the conjecture. We'll pick 1 or 2 conjectures and try to look at them and try to get an idea of how a conjecture should probably look like. I again I don't think I am the best at doing this. I'm still a student like all of you. It's just that probably I've done this for maybe a few years now to know a little bit about it, just a little bit about it. When I started off, I just thought anything that you just come up with should be a conjecture, but there's a way of stating a few things, which I realized in the last 2-3 years, actually. When I spoke to a few mathematicians, they said, what you're saying makes sense, but can you say it in a more mathematical form? So let me show you how a math paper looks like, and let me show you a few of my conjectures. Let's see. So ignore all these things. This is how a paper looks like. So this is currently what I'm writing: computational experiments on primes. There's an abstract, and there's supposedly an introduction that I might write, and then there are conjectures, and then there is some code, and then there is some conclusion and future, and there it ends. It's just 6 pages. You might wonder, is this all it is? Let me tell you that in general, the shorter a paper is, the more value people generally have towards it. They just want to read something short. Whatever is your idea, you present it in a very concrete and nice, tight way. Don't write too many stories. Don't write it like a novel. But whatever that is. So let's look at a few conjectures here. They're written in mathematical form, which might be new to some of us. Let's look at conjecture 2, which I think is not that hard to understand. Okay, let's look at this. It says, for every prime number. So before that, I just want to let you know that most of my conjectures, or at least the ones that I'll be discussing with you today, are things related to primes or number theory in general. Right? I might have a few things in other fields, but we'll not talk about that today. We'll focus on prime numbers, which I think is very intuitive for us to understand, because we all like to count and we like the arithmetic aspect of numbers in general. So for every prime number p greater than or equal to 5, let's pause at this stage. Let's see how this is written. So for every prime number p, we are calling each prime number as p. Just like how you assign a variable x, y, z, we're calling it p, which is greater than or equal to 5. 6 times p, 6p multiplication, can be written as something which we will not look at now, such that q, r are both prime. Okay, so what is that? You pick a prime number p which is greater than or equal to 5. So 2 and 3 are illegal prime numbers for us, which we will not look at this point. We'll only look at numbers which are 5 or greater than 5. 6 times p can be written as q squared plus r, such that q and r are both primes. Let's, before I completely feed this to you, I will wait for some time and let's try to read it, right? Let's try to understand it on our own, and if anybody has any question or thoughts, you can share it with me. If anybody wants to come up with examples on their own, you're recommended to do that if you already understood what the conjecture means, and I'll stay here for some time. I'll not say anything and I'll let you all think. Does anybody wish to say something? Yes. So I think a few people are raising their hands. So maybe the TAs can decide who can ask first. I'm okay taking any questions at this point.
Can you take it up?
Sure. Oh, I have to decide?
No, Ruhi, are you there?
Yes, I am there. Jay, why don't you ask your question?
So I didn't have a question. I had an example.
Okay. Do you mind holding on to that for just a second?
Okay.
I would love to hear your example. Maybe you can put it in the private chat to me if that's possible. I want to look at that example, but if you probably give that a little earlier, maybe somebody else who is still trying to understand the statement might be a little confused. So let's, okay, let me look.
Vihan, do you have a question?
Actually, I don't have a question. I want to tell something about the prime numbers. One time I was doing my class. In that, in prime numbers, if we multiply, I think something like that, multiply or add, I think multiply, we get a prime number. So into 3 into 6, 3 into 2, 6. 6 has factors 1, 2, 3, and exactly 4. So if we do for take any two prime numbers and multiply them, then the factors will be 4 of that number, the product.
Very good. That's a very good observation, and that's actually true. You pick two prime numbers and you multiply them together, that number will only have 4 factors, which is 1 itself and those 2 primes. And that's, you can easily show it using the fundamental theorem of arithmetic. I really like that observation. Okay, so I got an example from one of the students which isn't completely correct, but I think that's a good idea because the person is thinking in the right direction.
Excuse me, Raghav. There's another comment from Tanish.
Sure.
So what I think is that Q has to be 2. If Q is not 2, then like no other prime squared will be even.
Can I reply?
That's a very, okay, let's I want to address that question. So he says Q has to be 2. There are 2 primes, the Q squared plus R. He's saying Q has to be 2 because if Q is not 2, Q will be odd, which will make Q squared also odd. R is odd plus odd will become even. But I want you to see that we are not trying to write a prime as a Q squared plus R. We are trying to write 6 times a prime as Q squared plus R. So 6p will always be even no matter what p is, because 6 is even. So now once you have an even number, you want to split it. You want it as either a sum of an even number. You only want it to be, you can either have it as a sum of 2 odd numbers. I think that's the only way you can do it. Is there any other way to do it? No, you can only have it as a sum of 2 odd numbers. So then you would have to have Q and R as not 2. Let me look at the chat. A few people are sending me. Yeah, okay. Now I think I'm getting a few correct examples here, which is very good to see. Did everybody understand what the question by Tanish was? Why he said that Q has to be 2, why he assumed that Q has to be 2, and why it doesn't have to be 2, and it cannot be 2 as well? Unless Q and R are both 2, that is a possibility, because then you'll have an even plus even add up to an even number. See, we are starting with a prime number P, which is greater than 5. So we know for a fact that this P has to be odd. Do we all agree with this at this stage? P has to be odd, cannot be even. It's greater than 5. And I knew you guys would make such comments. That is why I said it has to be greater than or equal to 5. For people like you, for all those mathematicians who will keep looking at this, the moment you say every prime P, they will pick the worst possible prime and they'll try to disprove you. You have to make sure you put it in writing, which are the numbers you can choose. If you tell for every prime P, they will know that this will probably work for bigger primes and they'll pick these smaller ones like 2 and 3, which are not even proper primes because every other multiple of 3 is not a prime. I mean, it's what I'm saying is stupid, but whatever. So they will do that and then they will disprove. So you have to clearly say what prime you want to deal with. So we pick an odd prime and then you multiply it by 6, then you get a number and that you split it as q squared plus r. Okay, I'm getting a lot of messages now. Somebody's asking, why can't P be less than 5? Okay, good question. Exactly at the point of time we're discussing about why can't P be less than 5? Well, it's my conjecture. I don't want it to be less than 5. You have any problem? No, I'm just kidding. So it is to avoid this ambiguity. But I want you to know that when you come up with your conjecture, you have the freedom of defining the rules the way you want. As long as what you are defining works, nobody else can say, hey, why did you do this rule? Why are you only picking P prime? Why can't you do any odd number? You tell them, you make your own conjecture and you prove it for that. We are okay with that, right? I'm just kidding, but that's a very good question. So suppose you have P as 3, then what happens to 6P? 6P will be a multiple of 3. You agree with that? Because we're starting with P equals 3, 6P is a multiple of 3. Doesn't that make it a lot harder for you to come up with a prime square and a prime that should add up to a multiple of 3? Won't that be slightly harder? Can't believe nobody else caught the flaw in my logic. Any flaw in my logic? I'm trying to say that I cannot pick P because then 6P will be a multiple of 3 and then splitting it will be difficult. Does anybody have any problem with that? Good point. Whether P is a multiple of 3 or not, 6P will still be a multiple of 3. So that is not really a reason to not choose P equals 3. Why do I need P equals 3? I can pick any P, but when I do 6P, so just because it's a multiple of 3 doesn't mean it will be hard to split it, because you're picking it as a square of something and a sum of something. As long as you ensure that the sum of that or either of them are not a multiple of 3, they can still add up to form a multiple of 3. There's no problem with that. You can have two non-multiples of 3 to add up to form a multiple of 3, which is totally fine. So there is probably no particular reason why I did that. I actually don't know why. Maybe I tried a few examples and I felt that it was not working in some cases where it was 6 times 2 or 6 times 3 and things like this. So I think I decided to stick with what is this? 5 or greater than 5. It's actually something that I need to think about. I don't really recollect why I didn't want 2 and 3. Okay, now let's look at a few examples. I'll pick an example from the chat which somebody had given. They said, let's see, it's way back in the chat. Yeah, 30. They're saying 30 is 5 squared plus 5. 30 is 5 squared plus 5. So how do we start with 30? We make P equals 5. 6P becomes 30, right? So we have 30. 30 is our number which we have to split now. So then you get 30 equals 5 squared plus 5. So you have 5 and 5 as Q and R, which are 2 primes. Do you guys notice that this is very similar in structure to the Goldbach conjecture? We are coming up with an even number, which we are trying to split as a sum of 2, not primes exactly, but 1 prime and 1 square of a prime. So the style of the conjecture is quite similar to the Goldbach conjecture. But it's a lot harder to prove because the Goldbach conjecture itself is not known to be true. If you don't know if an even number can be split into a prime plus a prime, how do you even know it can be a prime squared plus a prime? Or how do you know it will happen for all prime multiples of 6 which are greater than 30? How do you know that? So it's a slightly different conjecture. But I wish to read this particular line over here. So somebody proved that every even number can be represented as a sum of a semi-prime and a prime. this is, as of now, one of the best results for the Goldbach conjecture. What is a semi-prime? A semi-prime is a product of two primes. The kind of numbers that Tanish mentioned, was it Tanish or was it somebody else? You take two primes and you multiply them together. That is called a semi-prime. So somebody has proved.
Sorry, question.
Yes, sir.
So when you say semi-prime, you are not referring to primes which are multiplied by 2 or 3, right?
That's also a semi-prime.
So if you say 6 is a semi-prime.
Yeah.
Like that. Okay.
Yeah. Any number which is a product of two primes is a semi-prime.
Okay. So it is not like pseudo-prime, a number which looks like a prime but is actually not. Okay. Got it.
Yeah. So pseudo-primes are numbers when you look at them at first glance, there'll be an odd number. They'll have this some 7 and 3s in the middle, which will give them this prime numberly feel. You'll add their digits. They'll not end in a 5. You see that they're not multiples of 3. So hey, this is a prime number, but then it'll turn out to be 29 times 37 or something like that, which those are pseudo-primes. These are semi-primes are numbers which are product of two primes. It's been proved that every even number can be represented as a sum of a semi-prime and a prime. So you have one prime and one you have semi-prime. And if you notice in my conjecture, we do have a semi-prime and a prime. We do have it in some sense. But we have a restriction on that semi-prime where we are saying it has to be a square. That has not been proved. It has been proved that you can have some...
Semi-prime, like our semi-primes are like two primes multiplied by each other, like.
Yeah.
Okay, got that. Then there
Yeah,
are a lot
just
of
a product of two primes. Yeah. So my conjecture is also talking about a semi-prime and a prime being added up to an even number, but there are a few constraints. The even number has to be 6 times a prime, which is greater than 5. And one of the numbers is a semi-prime, but it's not just some semi-prime, it's a product of the same prime to itself. Because a square of a prime is also a semi-prime, right? Because it's a prime times a prime. That's still a valid semi-prime, but we're dealing with the same number. So that's why it's a slightly different claim than what has been proved. This conjecture mandates the semi-prime to be a prime square. So why have I made this comment over here? Why have I written that this was proved? Because sometimes when you come up with something, it would help to show how it is connected to something which is already known. That way, the person who is looking at your work will think it is valuable because they say, oh, so this is a development on something which is already known. Rather than you just throw away something randomly, you try to connect it to something which is known. Okay, so that was one conjecture. I have a few examples here. One small example, which was given in the chat. And then I have a slightly bigger example. We have 114, which is 6 times 19 is 5 squared plus 89. Then we have 4398, which is 61 squared plus 677. Then we have a bigger example of this number. So that was one conjecture. Before we move to the full Q&A, I wish to show you one more conjecture, but not from this list, which is currently in a formal way. I want to show you something which is very dear to my heart, which is probably going to look stupid right now. It's the first list of conjectures that I made almost 6 years ago. So I have that original thing that I wrote. This was the thing that I wrote. It's 25 conjectures of a 15-year-old. So I wish to show you one conjecture from here. And let's see whether the cricket names are still there. This is Raghavendra N. Bhatt, 10th C, Madhav Krapa School, Manipal, India. This literally feels like a previous lifetime. And I haven't looked at this for quite some time. So this is a good opportunity. This was a good opportunity for me to retrieve this old thing that I had written on MS Word or something like that, or I don't know where I had written this. So let us look at one of the simpler conjectures, because most of these I don't think are true. Not most of them. I'm sure at least 2 or 3 of these aren't true. But let me pick one which is easy enough for us to understand and something which isn't too hard to read, because some of these are not written in a very nice way. Yes.
Sir, I saw one saying multiples of hat trick.
Hat trick. Okay. Okay, let's look at this one. This is, I think, an easy conjecture to understand. And what is the name? Multiple runs after the half century. So those of us who are cricket fans, half century is when somebody scores 50 runs, saying multiple runs after the half century. If you guys want, I can just read out the names of the conjectures because they're all related to cricket. But let's look at this conjecture. It says for every even number x, there exists a prime number p smaller than its half, such that x times p minus 1 is prime. One thing I want to point out here is, look at the way this is written. I'm not using any symbols here. I have a capital P to represent primes, which is a stupid thing to do, because actually the capital P stands for the entire set of primes. Usually use a small p to represent primes. And I'm using this star operator rather than using LaTeX. There's no brackets around x squared minus 1. I'm assuming people to know BODMAS. Okay. So let's look at the conjecture. It says for every even number x, there exists a prime number p which is smaller than its half, such that x times p minus 1 is prime. It's a very simple conjecture. Some of the examples, if your even number is 50, you pick a prime smaller than its half. So smaller than 25, I pick 3. So 50 times 3 minus 1 is a prime. If I start with 62, then I pick 7. 62 times 7 minus 1 is a prime. Or 74 times 31 minus 1 is a prime. This was one of my first conjectures. And I don't know whether I can prove it or disprove it, but I want to tell you one thing about this. This is almost really likely to work just because of probability. So why will this work? Because I'm saying you can pick any prime number which is smaller than its half. And for a given number, there are quite a few primes which are smaller than its half. The exact formula is probably complicated for me to talk in this particular session, but there are a lot of primes which are smaller than the number's half. Like if you start with the number 100, there are so many primes which are smaller than 50. So there is a very high chance that one of those probably can be multiplied and you subtract 1 and get a prime. So it's something that should probably work just out of probability. There's a very high chance that it works. There's a very low chance that it fails. Okay, so that was pretty much what I wanted to cover today. I'm basically, I could talk about more conjectures, but I don't want to do that. Let's just look at some of the names. Let's see. 10,000 hole with square cuts. There's one which says 10,000 hole with triple centuries. Okay. Then there is the force or power of the double ton. Double ton in cricket is when you score at 200. Let's look at what's my last conjecture called. It's called the reverse sweep. It's called the reverse sweep. And there is one called centuries without penalties. So at that point, I just wanted to be creative, so I came up with this. Okay, so I will stay back for some more time. And
there was one, Raghavendra, about something more than 10,000, which is a p square plus a, something like that, or a square number plus prime.
Yeah, it should be somewhere. I think it is going. I think it's also in that paper that I'm writing. But
was that any number more than?
No, any multiple of
10,000. Any
can
multiple
be expressed as a cube number plus a prime number.
No, any multiple of
10,000.
10,000 can be expressed as a cube plus a multiple of prime.
No, cube plus a prime.
Cube plus a prime. Okay.
Yeah, any multiple of 10,000 can be written as a cube plus a prime. Again, I feel that's highly probabilistic because there are so many cubes and primes, but that doesn't mean it shouldn't work, because if you look at the Goldbach conjecture, that's also highly probabilistic. If you're looking at an even number and you look at all its prime pairs which are small, there are so many prime pairs, there's a high chance one of them will work out. Anyway, let's see if that conjecture is somewhere here. 10,000. I think that was part. Yeah, 10,000 in tests. Here it is. Every multiple of 10,000 can be written as a plus p1, where a is a cube and p1 is a prime, or 0. Oh, I don't like this. Why do I have this exception here? I know why I have this exception. Whenever this multiple of 10,000 is a cube in itself, you write it as itself plus 0. That's why I have that exception. And I didn't know that exception when I did this in the beginning. Okay, so let me stop overloading you with all this material, and I will stop sharing my screen. I'll stay back to chat with you guys for some time. I apologize in advance if some of the material was too fast. I know I have a tendency to speak really fast when I like what I'm talking about. So I apologize for that. And I'm also sorry for not being able to look at the chat throughout, because when I was sharing my screen, I couldn't really see that. Let's see if somebody has any questions. Yes, somebody has a doubt.
So Ruhi, you can call out names for those who are raising hands, and then they can ask.
Okay, sure. Siddharth, you can ask your question.
Okay, so my question is, Raghav, will you share that 25 conjecture by a 15-year-old that file with us?
Sure, I would love to, but please don't judge me. I think it's
I'm
very
not going to judge you. I just want to see that.
sure. Now, the reason I say it is when I look back at it, I feel it should have been way better than that. There are a lot of mistakes in it, there are a lot of typos and all of that. But a part of me doesn't want to change it because I want to leave it as it was, you know. So I'm going to, I can actually send the PDF here on Zoom.
Yeah, thanks.
No problem.
To see
I wanted to do that. Thank you for reminding. It was in the back of my mind. I just forgot about it.
Okay, thank you, Siddharth. Sai Arun Prasad, you can ask your question.
Raghav sir, there was a question you said, there was one of the conjunctions where you said that for every prime number that is any number x divided by 2, and the prime numbers can be written as something that is take a number x and divide it by 2, that will be, and take prime numbers lesser than x by 2. After that, if x multiplied by p, that's the prime number, minus 1 is the prime number. But what if x is equal to 5?
Let me look at the statement of that.
5 or 4?
Yeah, I probably was referring to
Both of them. 5 might work, but 4 won't. Yes.
You're right. Some background noise. Yeah, sorry. Yeah, so that's what it was written very immaturely, because you don't even have a prime which is smaller than the half of 4. So I think I'm assuming that those are numbers which are greater than 10 or something like that. That's why I said it's not very mathematically written. There are a lot of exceptions to most of those conjectures. I think I probably tried it for the larger ones and I've just written it as it is. But in reality, yes. Although if I said lesser than or equal to half, I could then do 4 times 2 minus 1 and 7, it would work. But for 5, it wouldn't work because there's no... then it
will still work for 2.
What was that? I'm talking about only even numbers, by the way. So 5 wouldn't be a part of that. Yeah, I'm only talking about even numbers.
Oh, okay.
So
4 will work though, because divided by
2 minus 1. Yeah, we can consider 2 to be lesser than or equal to the half of 4. So, and for 2, it won't work because 2 itself doesn't have any prime smaller than it. Unless you want to consider 1 to be a... I could change the conjecture to be non-composite.
Prime. 1 is not a prime.
No. I could change it to be non-composite. Then you can choose 1. Then you can do 2 times 1 minus 1, which will be 1, which is still non-composite. But again, let's assuming numbers which are greater than 6. Yeah. Yeah, we have 15 more minutes, I think. Yeah, so I will take 2 or 3 more questions. We don't have to wait the full 15 minutes, but unless somebody has any other question.
Yes, Anushka, you can ask your question. Anushka?
Yeah, sorry, I couldn't unmute. Raghav sir, I don't remember the name of the conjecture, but it was the one you were explaining in the very beginning. The for every prime number p is greater than equal to it was I'm really sorry, I can't remember it, but it was one in the collection of conjectures, and it had something to do with the x. Yes, it can be expressed as x into p minus 1, that one. So I know it wasn't rigorous, but what happens when x is equal to 2?
Oh yeah, I think I just took that question right now. We are assuming numbers which are 4 or larger than 4, and we are assuming for 4 we can use 2, because everywhere else it has to be greater. Otherwise, I hadn't mentioned the exception for 2, because 2 itself is a prime and there's no prime which is smaller than 2. So we are assuming numbers greater than that.
Okay, sorry.
No problem. Good question anyways.
Yes, thank you, Anushka. Tanish, you have a question?
Yes, so I wanted to ask, like, have you ever tried to prove any of these conjectures, or uh, like,
Yes, I
like,
have.
discuss
Sorry.
it with your teachers or anything?
Yeah, there are quite a few of them which I have proved, which I have not presented here today, which I might be presenting in another session in some other workshop. I think very close to this end of the month or whatever that is. Uh, these ones have not been proved because they are very difficult to be proved in general. And some mathematicians have looked at these conjectures and they feel that whatever tools we currently have might not be sufficient to prove this at all. For the very reason the Goldbach conjecture itself isn't proved, right? So that's probably one of the reasons. But yes, I have tried. Yes, Vinay sir.
Sorry, I just a clarifying question. So, what, Tanish, I don't know whether you are asking whether these among any of these 25 conjectures he has discussed with somebody, or has he discussed conjectures in general? And
No, I mean the conjectures he has made.
he has made. Okay.
I have made, yeah. So I have some other conjectures which I didn't talk about today, which are related to numbers which are not exactly primes, but slightly different numbers to primes. And some of them, yes, I have been able to prove. Most of
So,
these are lying in the same bucket as the Goldbach conjecture because they deal with splitting of numbers and randomization of primes, which are very difficult to prove currently.
so Raghavendra, if I'm not wrong, none of these 25 conjectures that you have shared are proved.
Some of them are disproved.
Some of them are disproved. So okay. So
Some of them
that's
are
again
the last one has been proved. I think
don't reveal which ones have been disproved. It's going to be a good pastime for these guys to work on them, and maybe they can become famous if they prove some of them. Right?
Definitely.
Okay.
Yes,
Proofs
honestly
also
speaking, I
been
don't know which ones have been proved or not. The last one I felt had been proved, might be true, but in general, I don't really know which ones have been proved or not proved. I think one of the professors in my older university had proved the last one, but I have to look at that. I don't know whether he proved it or disproved it. See, this is a similar situation to that guy who did that Goldbach conjecture thing. I don't remember because there were so many. No, they haven't been published. So the paper which I showed you is something that I'm currently working on. I did communicate with the journal and they wanted some additional coding or whatever. They liked some of the things that they saw, but they wanted some more things. So they required a revised draft of the whole thing, which I'm currently working on. Hopefully very soon, yes, it might be. I'll let you all know if that remarkable thing happens.
Okay, Raghav, there are a couple of more questions. So, Parth, if you want to unmute yourself.
Yeah, so in this you have written some code. So these codes are for what? In Python or C++ or Java or what?
Sorry for not mentioning that. So when these things cannot be proved, what you do is you resort to this brute force method of checking something. You try it for a lot of numbers. Now that is not how mathematics works. There are very, very famous things that work for more than 10 trillion things and then suddenly stop working. But at this point, for many, many things in math, when you don't have a lot of evidence, you try to present some data. So I write simple codes in Python where my conjectures are tested on numbers all the way up to 10 billion or sometimes all the way up to 10 trillion, depending on the complexity of the conjecture. If it involves squaring and checking, sometimes it will take longer because some of you who might be knowing how computers work, if the operation to do the thing will take longer, then obviously the code also will take longer to reach 100 million or 10 billion or something. Which is a simple conjecture which doesn't involve too many computations to check. It can go very, very far. So I check it and I don't find any counter examples all the way up to a huge number. And then I assume it to work, which is not the way to go about things. But when it's a conjecture, that's the best you can say that I've tried this so far and it works. So at least I have something which works at the start. If you wish to disprove it, either tell me that it doesn't work later on, or you can prove that it works later on. So I'm making life a little bit easier for people who want to prove it. They don't have to prove that it works for everything. They just have to prove that it works for numbers larger than the ones that I've already checked. Right?
How huge are the huge numbers that you're talking about?
More than 1 trillion at times. And that's very small when we talk about infinity. But in this case, sometimes those numbers can be useful because ultimately these things deal with patterns in primes and some sort of probability when it comes to primes. And although primes are randomly distributed, there is an asymptotic formula to predict how many primes should lie smaller than a given number. So there is some sort of pattern. The sieving techniques do usually eventually end up having some sort of pattern to them. So if it works for a large number, there is some chance that it can keep going on for very long. At least when it comes to primes, there are very few conjectures that have been disproved later on. The conjectures that I'm talking about are not related to primes. There are other things in number theory, like the logarithmic integral or something like that, which people assume to be true up to some point, and then suddenly the value changes. So yeah, in general, that's how it is. But with prime numbers, if it works up to that number, there is a high chance it keeps working, because primes don't stop, squares don't stop, cubes don't stop. So maybe those three people will keep moving in tandem and continue their beautiful patterns, which are not yet visible to us mere mortals, but somehow they are working somehow in that abstract universe. So we, as a mathematician, we don't do anything. We just watch them do their thing. Every number is existing in some abstract dimension of the universe. It has all its properties. Pi is extending as and when we speak, right? √2 is going on and on and on. Negative square root of -1, something, it exists in some imagination. We just try to watch them and make sense of them. They are working already. The Goldbach conjecture is already working. There is some proof to the Riemann hypothesis or something which contradicts the Riemann hypothesis somewhere in the universe. It is our duty as students or as admirers of mathematics or as professors to access that energy somehow. And the only way you can access it is if you're not scared of not accessing it. That's why I said shouldn't be scared of being wrong. I'll take one last question and then we can wind up for today. In advance, I want to tell you all that it was a great pleasure. I had a great time. This is something that I really like doing. I think I had a similar session last year around this time. So it feels really good at the end of a year, at the end of a semester, to have a nice late night talk to students in India. There's nothing better than it. Trust me. So let's take one last question.
Yes. Sai Arun, you can ask your question.
Sir, has the first conjecture in your 25 conjectures proved?
The first one. That's one of the most obvious ones. I think every odd number greater than 7 can be written as a multiple of 6 plus a prime. Yes, I think this has been proved. It has been proved. Yes, it was one of the things which even my school teachers felt was not that powerful, but I just kept it because I liked it. But quite a few mathematicians have proved it. Yes, it's probably not that hard to prove. I don't exactly remember the proof now, but I think I did remember it at a point of time. Okay, it was a great book. I skimmed it and I enjoyed it a lot. Although I don't know. Oh, sure. Thank you so much. I hope you enjoy that. You can also check out another book that I've written. It's called Math, A Subtle Language of the Universe. It's actually a book. It doesn't have too much of math. It's more to do with articles and things that I like in math, how math should be taught, why people find it hard. There are a few puzzles in the end, and might be a good read. And I wish you guys all the best in your journey in mathematics. At any point of time, if you wish to discuss something, I'm available via email. So I'm just going to put my email here in the chat. But don't email me Happy Deepavali, sir, Eid Mubarak, and all of that. Send me things which, if you're actually, want to discuss about mathematics. I wish you guys all the best. Just don't be afraid of coming up with ideas. Don't be afraid of asking questions. There's this famous quote: if you ask a question, you might be a fool for a minute because everybody might laugh at you. But if you don't ask a question, you'll be fool for the rest of your life until you get the answer. So keep asking questions. Don't be afraid of innovation, creativity. Aim for the skies, right? If you aim to climb the Mount Everest, you might at least climb 1/10 of it, which is still an achievement. But if you only aim to climb 1/10 of it, you might climb 1/100th of it, which many other people might also do. So setting your upper limit is in your control. And as long as you keep it really, really high, you are going to do great things. And I'm sure all of you here will do incredible things. I'll tell you this much. At your age, I was nowhere close to what you are. So I think that itself is enough for me to think that at my age, you can be way, way, way more than where I am now. So I wish you all the best. Thank you, Vinay sir, for this opportunity. And thank you all for being here patiently, and all the best for the rest of the camp. I know this is your last day and I know how it feels. Last day of any camp done by Vinay sir. It's not a nice experience. I've cried more often than I've laughed in most of the camps. But I'm glad that all of you could attend this workshop, and I hope you all learned a lot. Thank you so much. Bye-bye.
Thank you, Raghav. All of you just stay back. Just stay back for a moment. Ruhi, would you like to share
Yes.
something before we close?
Yes, thank you so much, Raghav Dada. I have known you for the past 1 year, and again, on behalf of all the students present here, I would like to thank you. This discussion was extremely fascinating, and it's great that we got to be a part of your end of the semester celebrations. As Vinay sir said, you are extremely passionate about mathematics, and I have seen it on multiple occasions throughout the past year. Every Sunday for him, every Saturday night, for the past 2 or 3 years, I think, he has been taking, discussion sessions for a couple of students, and he stayed up late and taught us RN numbers, advanced number theory, and he also spoke about his college life and experiences. He's a great storyteller, so anytime he starts to speak, everybody is engaged and listening to him. I have learned a lot from him. I usually hate waking up early on a Sunday, but whenever Raghavendra Dada was taking a class, I had to, like, I was the first one ready and awake. Today when you spoke about creativity, it was so relatable. Like the way you gave the anecdotes of Steve Jobs, J.K. Rowling, Thomas Edison, I was very inspired, and I am definitely sure that all the students over here are also going to remember you. And of course, your conjectures, the conjectures, how beautifully you've written them today, and how I wouldn't say not so beautiful, but yeah, that how you had written them. When you were my age, I think. And like you said, it is hard to say goodbye from a camp, and we all, I mean, I'm sure all the students here are feeling that right now. But thank you so much. It was a wonderful session, and I enjoyed it a lot, and looking
Thank you so
forward to seeing you in the future and attending more sessions of yours.
Thank you so much. Thank you so much.
Thank you, Ruhi. Thank you, Raghav, for inspiring all these young minds. I'm sure you have lit the spark and they'll come chasing you and be ready to face the consequences. Thank you so much. Raghav, if you have 2 minutes to stay back,
Sure,
that would be great. Yes.
Sure. Yes.
Okay.
It's possible.
Thank you all participants. We'll see you in the next